Blockchain network and technology. This section delves into the technical structure of blockchain networks, explaining how they function, the role of consensus in maintaining integrity and trust, and the architecture that supports blockchain's unique characteristics. Anatomy of a block. Structure. A block in a blockchain is a container data structure that aggregates transactions for inclusion in the public ledger, the blockchain. Typically, a block contains a header, which holds metadata, and a body that contains transaction data. Header includes the previous block's hash, a timestamp, the nonce, and the Merkle tree root hash, which summarizes all the transactions in the block. Body lists all the transactions validated and included in the block. Example, in Bitcoin, a block structure facilitates the process of mining and transaction verification, ensuring the security and continuity of the blockchain. How transactions are recorded on blockchain. Transaction initiation. A user signs a transaction with their private key and broadcasts it to the network. Verification. Nodes verify the transaction's validity, including signature authenticity and the sufficiency of funds. Transaction pool. Valid transactions await in a pool until they are picked up by a miner to be included in a new block. Block creation. Miners assemble transactions into a new block and compete to solve a cryptographic puzzle. Consensus. Once a miner solves the puzzle, the new block is broadcast to the network. Other nodes validate the block and add it to their version of the ledger if it's accepted. Understanding blockchain consensus mechanisms. Consensus mechanisms are core to blockchain technology, enabling trustless and decentralized transaction verification and block addition. Proof of work. Miners compete to solve a complex mathematical problem. The first to solve it gets to add the block to the blockchain. This mechanism secures the network but is energy intensive. Bitcoin and Ethereum are prime examples. Proof of stake. Validators are chosen to create a new block based on the amount of cryptocurrency they are willing to stake or lock up as collateral. It's more energy efficient compared to POW. Ethereum 2.0 aims to use POS. Delegated proof of stake, a variation of POS, where token holders vote on a select number of delegates to validate transactions and create blocks. EOS uses DPoS. Popular consensus algorithms, proof of work, proof of stake, and others. Proof of work ensures security through computational work, deterring attacks by making them economically unfeasible. Proof of stake aims to reduce energy consumption and increase transaction throughput by selecting validators based on their stake. Others. Practical Byzantine fault tolerance addresses the Byzantine generals problem, allowing a distributed network to reach consensus even if some nodes fail or act maliciously. Hyperledger Fabric employs a variant of PBFT. Examples. Bitcoin and proof of work. Bitcoin's blockchain uses POW to secure its network, where miners solve cryptographic puzzles to validate transactions and create new blocks. Ethereum in transition to proof of stake. Ethereum is moving from POW to POS in its Ethereum 2.0 upgrade, aiming to become more energy efficient and scalable. In practice, supply chain management. Blockchain can provide a transparent and immutable ledger for the supply chain, ensuring the authenticity and traceability of products. For example, Walmart uses blockchain for tracking produce from farm to shelf. Healthcare. Patient records can be securely stored and shared on a blockchain, improving data accuracy and accessibility. Estonia's health system is an example of blockchain in healthcare. Blockchain technology's network and architectural principles provide the foundation for its decentralized, secure, and transparent characteristics. Understanding these aspects is crucial for leveraging blockchain in various applications, from cryptocurrencies to broader industry use cases.